So in practice, this combination of things. So look, we resolve foo. This was the local guy. We get the local one. Now list, we never defined in the user namespace. In fact, all the Clojure functions are auto-imported into the user namespace, which means if we resolve list, we see it says Clojure list. It's the system one, which is neat, which means if we write a macro, right, that says backquote list foo x, right, and expand it, look what we get. Data structures with symbols, but the symbols have qualifiers. No matter what namespace I resolve this in, Clojure list resolves to Clojure list. So this system actually solves a lot of the hygiene issues from being a list one, separating symbols out. I don't want to spend any more time on it, but I will say I think this goes a long way towards that. I also have auto gensims. That's not to say you will never call gensim. You will, but you'll have to be writing a more sophisticated macro, in which case you know what you're doing already. Clojure has pervasive destructuring. Destructuring is pretty cool, I think. Pattern matching is all the rage, and I'm not exactly a fan. I like the destructuring part of pattern matching, but I don't like the switch statement part of pattern matching. So Clojure has destructuring, but it has it everywhere. But like the other parts of Clojure, destructuring is based around abstractions. It's what I call abstract structural binding. So in let and loop and fun and binding lists, really anywhere where you're doing bindings, or anything that's built on these things, which basically is everywhere you're doing bindings, you can use data structures where symbols would go. And you're going to get destructuring. So you would say let A1 or let A42, right? Now instead of saying A, you can put a data structure there, and there's interpretation. Two interpretations. Okay? If you have a vector as your binding form, it will destructure anything that's sequential. Okay, so it's anything that implements the sequential interface. You can destructure lists and strings and arrays and anything that supports nth. And it will pull that apart. Of course, it will be a vector with names in it, and those names will be bound to the parts of the thing. I'll show you this in a second. You can also have a map as a binding form, and that will destructure anything that's associative, which includes maps and vectors. Vectors are associative. You could do a map-style binding form and get the 17th thing out of a vector and call it Fred. So unfortunately, I think these examples are a little bit too verbose, but this first one we might be able to understand. So let, and there's not a simple name here, right? The first thing, it's a vector. So we're going to say we're going to bind A to the first thing, B to the second thing, C to the third thing, D to the rest. And we're going to call the whole thing E. And then we're binding that to a literal vector of numbers. So A, B, C, D, E. That's really cool. This nests, so this is a vector with two vectors where we're naming the parts inside the vector, and then we're passing a vector of two vectors, and we're naming the parts in. So that all does the right thing. This one's particularly wordy and too large. But the idea here is named key, name key, name key, same as thing, defaults, et cetera, et cetera. We bind it, we pick the pieces out, we can get the defaults in, we can name the whole structure, A, B, C. But it didn't have B, right? So we got the default. And M is the argument. Or says if you don't get the key, use this as the value.
You said destructuring works for functions.
Yes, you can put these things in function arguments, yes.
Optional arguments, if you use or.
A certain flavor of them. Right, somebody would have to, if you're using OR, somebody has to be passing you something associative, right, which the argument list isn't by default. But if they pass you a map, they could get defaults that way. You can build all kinds of cool things with this. They nest arbitrarily. So if you do a vector destructure or map destructure, and then for one of the arguments you destructure that key as a vector, you can pull all the pieces out. And if you stare at this long enough, you can figure out what it says. But the idea is that they nest. They nest arbitrarily without limit, and it's very powerful.
There's also the keys
Yeah, it's not even on here. There's other sugar that lets you avoid saying AA, BB, CC. If you want the same names, you can just say keys ABC, and it will pull them out. Similarly, you can pull out strings that way or symbols that way. So there's lots of power user features inside this. But the nice thing is, it's every place. So polymorphism. I said Clojure's not object-oriented, but Clojure's not anti-polymorphism. I'm very pro-polymorphism. I have two fundamental ways to do polymorphism. One is the Java way, right? You have interfaces. All the abstractions in Clojure are defined in terms of interfaces. The nice thing about doing it that way is it's a bridge to Java. If you want to allow extension via Java, Java can do that. Clojure can also do it. Multi-methods are the other way. That's kind of Clojure specific because Java doesn't have this kind of power. But what I wanted to do was avoid marrying dispatch to types. I'm sort of tired of types. I'm tired of having like these rigid type systems that that really incur a lot of accidental complexity for you. Every time you make a class, you have like all this complexity you don't necessarily realize anymore. And fixing valuable features like polymorphism to type system, which usually you only get one taxonomy for your arguments. So what Clojure's multi-methods are is a complete generalization of dispatch. What is generic dispatch? There are these arguments. I don't want to hardwire what happens when you call this function with these arguments. I want to do something specific to the arguments, right? In Java and C#, we're going to do something specific based around the type of the first argument. Okay. In Common Lisp, we have more flexibility. We can use the types or the values of any of the arguments. But it's still a hardwired heuristic, right? Unless you get into CLOS, underpinnings, you're still saying it's either types or values, and there's an order dependency and all this other stuff. But the reality of it is, it should be an arbitrary function of the arguments that determines what your method is. And that's what it is in Clojure. Okay? The dispatch function is an arbitrary function of the arguments. You want to have a multi-method? Give me a dispatch function. I don't care what it is. That dispatch function will return different values for different argument sets. I don't care what they are. You can associate actual methods with those values. I don't care what they are either. Have at it. You want to build single dispatch? Fine. You want to build CLOS style dispatch? Fine. You want to do something that compares the values of arguments? Go for it. You want to do something with the first and the third and one of the middle guys? I don't really care. So how does it work? You're going to give me a dispatch method, a dispatch function when you define the method. When I'm called, I'm going to call it on the arguments to get a value. They're going to look up and see, have you associated a method with this value? If you have, I'll call it. If you haven't and you've provided a default, I'll call that. If you haven't defined a default, you'll get an error. So this is what it looks like in my silly bunny example. The key thing to remember here is, so we're going to define a multi-method called encounter. And the dispatch function is take two arguments and pull out their species and return a vector of the two species. The trick you have to remember here is that keywords are functions of associative things. So those are two function calls. The species of the first thing and the species of the second thing. So we're faking types, although it's not the type of the first thing and the type of the second thing, because you only get one type. It's an attribute of the first thing and an attribute of the second thing, which means you can have other methods, multi-methods with different taxonomies. You could look at metadata, which I haven't talked about. You could do whatever you want. So in this case, we're going to pull out the species. So we encounter, if the dispatch value is bunny and lion, then we run away. If it's lion and bunny, then we eat it. Lion, lion, they fight. Bunny, bunny, they mate. Right? Then we define a bunch of literals. B1 has a species of bunny, and I don't care what else. I don't care what type it is. I don't care how many other attributes it has or anything. I don't care. I shouldn't care. And I shouldn't dictate to you that it be this particular type in order to interact with my API. That has to stop, right? Let people just glom stuff on so they can talk to you and not have to be something so they can interact with you. So
can you implement the map interface as you used to implement the map interface on what you have? Like you can pass in something that has an attribute that's a species that's stored in a different way, and then when you call species on it.
absolutely. I don't care, right? The way keywords act as functions is they look themselves up in the thing using the map interface. Does it have to be a map? No. You could have species 1 and species 2, and you could pass 2 vectors. That would work. You know, whatever you need to do. So then we define a bunch of data, and then the encounter things do what you want. I haven't had time to update this slide, but I've enhanced this system substantially by making it such that the values that are produced by the dispatch methods are compared via an ISA relationship, which will work for equality. 2 things that are equal will be ISA. But it also allows you to define relationships between really any names as hierarchies. It's called ad hoc hierarchies. So you don't need to have hierarchies only in types. You can just have hierarchies. You can say, colon square is a colon rectangle. You just tell me that. And then you could do this dispatch and say, if it's rectangles, do this. And if you pass squares, it'll work. Not types, right? Why does hierarchy have to be in types? Why stick it there? It's a dungeon, right? So hierarchy is about, excuse me?
Sorry, it's an ad hoc hierarchy.
Ad hoc hierarchies.
Per method.
No, it has nothing to do with methods. It's just you could leverage them here because the multi-method system uses ISA to determine what happens.
What's the performance tip of using multi-methods versus regular?
It's a hash table lookup, right? So all that hierarchy stuff is looked up once and cached. So, and then it will track any changes to the hierarchy system.
The function call and a hash table.
Well, yeah, the overhead is a hash table lookup. The extra.
There's an extra function call.
An extra function call and a hash table lookup, yes. It's not bad.
So if you're using the ISA test to
Yes,
compute applicability of the multi-method,
yes.
don't you have ambiguity based on method that
You could. Let's just talk a little bit about that. I'm sorry I don't have it on a slide. So ISA works between any 2 names. You define what the relationships are. Okay? Then you say, well, what if I had a vector of these and those? Vectors do a per guy ISA. Okay, which still begs the question, there could be ambiguity. Yes, there could be ambiguity. For instance, you could use Java interfaces to do dispatch. And something could implement 2 different Java interfaces. So which one do you use? If I get an ambiguity, I will tell you when you first call it, and it will fail. But you can then tell me, prefer, for this method, prefer this to that. And that will resolve the ambiguity.
So you actually test for applicability of every method that we define, and then
No, that only happens once. Once I get it resolved once, I cache that. So it's just a hash table lookup by value. I see the same dispatch value, which is the result of the dispatch method, and it's hash table lookup. If I fail to find it, now I have to do the work. If I do the work and find an ambiguity, I'll tell you. If you want to resolve that ambiguity, you can by saying prefer this for this method, prefer this to that. Prefer this interface to that one, for instance, or some argument set. It ends up being a pretty good compromise. You?
So is this similar to the predicate dispatch stuff?
What it's missing from predicate dispatch, which I really haven't been able to figure out how to do fast, is logical implication. Right? A real predicate dispatch should know that being less than 10 implies being less than 100. But this is not a predicate dispatch system. But it's pretty powerful and very general. Clojure supports metadata. Right? This is the ability to attach data to any value that does not constitute part of the value's value. It's about the value. It's not a component of the value. So it's orthogonal to the logical value of the data. You could have a vector, and you could say, I got this vector from Fred, or I found it on the internet, or I last read it 3 weeks ago, or anything else you want to say about it. That's not part of the value. Right? If it's a vector of 1, 2, 3, it should still be equal to 1, 2, 3. It's just you found it on the internet instead of, pulled it out of the database. So it does not impact the equality semantics. You don't see it when you do any operation on the value. But it allows you to adorn values, and it's a very important thing that's extremely hard to do in most systems, which is track, trustworthiness or age or validity or source or anything else. So you have the ability to attach metadata to all the Clojure collections and to symbols.
So, but the namespace, how would this impact the namespace?
Has nothing to do with it. It's attached to values.
Yeah, so the things that are in the namespace is not values, they're vars.
Vars have a separate notion of metadata. This is really the real
Right,
deal.
If I want to have metadata, if I want to have these keys.
You can attach metadata to vars, but this example is not. This example is about real value operations. Vars are not values. Vars are references.
Right,
So they have
sure.
separate semantics for metadata, but they do have metadata. But I don't want to talk about that right now because it's too confusing.
Why can't I just do metadata in Common Lisp and say, we have an object and then there's this hash table that maps the object to, where
Everybody has to know about that hash table. It doesn't flow through your call chain. Nobody can go and inspect it. They have to play. Metadata, you don't have to play. And a real hash table where everybody had their metadata is a concurrency disaster. Right? It belongs on the objects. It should flow. It should be copyable. And if you do that, it has to be associated with identity. These things are associated with values. Right? I could have 1, 2, 3 and then say I found it on the internet. I could have 1, 2, 3 and say I got it out of the database. What am I going to put in my global hash table? I'm in trouble. I have to put the identity of these things. But I don't want an identity system. I want a value system. And I can't have a hash table by value because they're the same value. And I can talk more about it later, but it wouldn't work.
Is this implemented using Java annotations?
No, annotations are properties of like of
It's kind of like
stuff.
that, right? It's also
Not really.
That's attached to the thing. and
Not everything. It's attached to the class stuff usually, not to every instance.
attached to code.
It
Yes.
seems like this would work well with a Ledger store, for example. If you needed to, as in your example, you were logging something, you needed to persist it in the database and bring it back. It avoids a lot of that overhead and concept mangling that would happen.
In real systems, I need this all the time. As soon as you have a big enough system, you find you need this kind of thing all the time. I have this huge calculation stack, right? I sourced it with some data. I mean, I work on the selection system, so I sourced it with some data that was from counties, right? But the data looks exactly the same as data that comes from precincts. Now I'm in the middle of a calculation. Do I have to say precinct, map of this, county map of that? I mean, putting it on types is wrong. It's just where I got it from. So I can flow that through. So essentially, any of the Clojure data structures support the attachment of a map of metadata, and you can use it for whatever you want. Clojure actually uses metadata in the reader. You can adorn your code with metadata, and you can talk to the compiler that way. In fact, that's how you give hints to the compiler, because there's literal support for metadata. So let's look at this. We can define V. It's the vector 1, 2, 3. Then I can say trusted V is V, same value, right, with this metadata associated to it. So one thing we know about with meta is what? Returning a new value, right? Because this actually can't be the same V. Then we can look. This caret is the same as saying meta of the thing. The metadata of trusted V is trusted. I mean, the source of the trusted V is trusted. The source of this thing, we don't have one. It's great. And caret, yeah, is reader syntax for meta of blah. Most of the things like assoc or whatever will build only on the first guys. They won't automatically incorporate. But all of the operations are metadata preserving. Okay, I can't really properly combine metadata. I don't know what it means, so I can't do that for you. But it's really useful.
You have a sequence and you take the first thing, then does that first thing have the metadata or something?
Probably. I mean, when you're adorning with metadata, you don't want to have little pieces of metadata on sub-pieces of all kinds of things. It's not that meaningful. You're usually attaching it to things whose contents are going to be consistent, or you're going to be responsible for adding or removing. And those additions and removals will produce new values with the same metadata. So they're metadata preserving. That's sort of as far as I'll go. And anything beyond that, you can do. Okay, let's get into some of the meat. Now, this is an important part of the talk because everybody in every language is facing this. Your programs, are they ready to run on 600 cores at one time? Are they going to use them profitably? I don't think so. But that's coming. What they're basically saying is these cores are not getting any faster. We're just going to give you more of them. Making use of them, your problem. Software developers. Hardware guys are punting. Punting. They left us out here. So I want to be clear about what I'm talking about in this part of the talk when I mean concurrency, because there's a bunch of different things. We're talking about interleaved execution. And now, of course, there was always threads, and there's ways to do green threads and pretend. But the reality is we're getting real interleaved execution now. Multiple cores means really two things are happening at the same time. We want to avoid seeing inconsistent data or creating inconsistent data, right? And as the complexity goes up, as your units of work involve more things, it gets more and more difficult to keep consistent, especially if you're using locks. There are also a whole other sets of concurrency things that have to do with parallelism, right? I want to do this one logical operation, and then in the background, this vector, matrix multiply, just put it on all these cores. I'm not talking about that right now. Java has a really nice library coming up in Java 7 for doing that kind of parallel math, and Clojure has a very beautiful wrapper for it. So here I'm talking about task-level parallelism. Most typical applications are going to try to leverage these cores by setting up a few threads to watch the web interactions, and then another couple to deal with the database, and maybe you have some streams coming in from this data source, and maybe you have a couple of calculation engines that you're going to use. That kind of task-level parallelism is what we're talking about here. So, this is my message. I don't care what language you're using, except if you're using something like Haskell or something already very purely functional. If you're using a system where you're using objects or shared data structures that are mutable, it is not going to work. It is not going to continue to work. You absolutely have to find some different way to do it. I think object-oriented programs, when they get to a certain size, are just spaghetti. I've never seen one that grew indefinitely and kept, being maintainable. So it's just a new spaghetti code. It's all object-oriented, but it's still a disaster. It's very hard to understand a program, even an object-oriented program. Once you have all these relationships, once you create a graph of interconnected changing things. But one thing's for sure, whether or not you agree with that, from a concurrency perspective, it's a disaster. And unfortunately, it's the default architecture of all of these languages, including Common Lisp. Right? You create objects, you get these mutable things. And it ends up that even if you know this and you say, well, I want to take a different approach in my applications, doing the right thing is really hard because it's not idiomatic. It's almost anti-idiomatic to, for instance, try to do immutable data structures in Java, for instance. So, although I did, that's what I'm giving you in the library that underlies Clojure, but it's you look at the Java, you're like, wow, that's nasty. So what happens now? Even if you're using a Lisp, one of the more cutting-edge Common Lisps that has threads and everything else, chances are good they have these same old, concurrency constructs that people in Java and C# are already saying don't work. So copying those is not really moving forward. What do you have? Applications have direct references to mutable things, right? And what could you possibly do in that context? It's essentially each program was written to be imperative, like I own the world. Each part of the program, I own the world. Okay? When you don't own the world, right, you either have to stop the whole world, that doesn't work, or somehow somebody has to preserve your illusion that you see the whole world. And doing that with locks is incredibly difficult, in particular because accomplishing that is completely convention. You have to have meetings. You say, this data structure is going to be looked at for multiple threads. If you're going to touch it, make sure you lock first. Okay, and then you have all this complexity. Well, what if I'm touching data structure A, B, and C? Well, you have to grab the locks in the right order, or you're going to deadlock. What if I'm only using C and B? Well, you still have to grab all three. Or maybe we'll have this global lock, and our concurrency is going to go down. It doesn't work. If you're just starting to do this, just skip to the end. It doesn't work. It doesn't work. I could save you years of grief, headache, and nightmares, because it's a nightmare. I've been doing this in C++ and then C# and Java for 20 years. It just is awful. You cannot ever believe it's working. So, what do? Instead of that, we're going to say we're going to have indirect references to immutable persistent data structures. So this ref notion, it's kind of like standard ML's ref notion. If you're going to have something mutable, you're going to have to call it out. This could change. All right? And then Clojure has concurrency semantics for those references. So those references are like cells. Right? All they're going to do is point to some bigger immutable aggregate. And if you're going to want to change those cells, because they can change, you're going to have enforced concurrency semantics. And your programs in Clojure do not do any locking. So this is what it looks like. in the old school. A bunch of parts of the program are pointing to the same block of memory. The problem fundamentally is this. Object-oriented programming done the traditional way unifies identity and value. You want identities in your program. You know, like tomorrow is going to mean different things as your program runs and runs and runs, right? So you want that identity, but the value of tomorrow or today's date or the time is something that's going to change. Right? Unfortunately, when you say the identity of this thing is the address where we're keeping its value, you're game over. You can't do the right thing. Anything can change at any time, and the consistency problem goes to the users. So what do we do instead? We have the programs refer to the identity, and the identity is that cell, okay, that reference. And that, in turn, points to some immutable aggregate thing. Could be a Clojure vector or map or any of the Clojure stuff. So now we've separated identity and value. If you want to obtain the value, you need an explicit dereference. Okay? At that point, you could have a pointer to this. 100 people could have a pointer to this. Is that okay? Sure, this can't change. It's immutable. Have at it. You want to look at it from 100 threads, 600 cores? That's going to be great. That's going to perform well. Because there's no locking required to look at the value. All right? So we're going to explicitly dereference. The values can never change. You could never see an inconsistent value because they don't change. Somebody's going to make a consistent value, stick it in there. You pull it out, it's consistent. Objects don't change in your hands. So what does it mean to do editing? Okay? Well, we've already seen, with all these data structures, we make new values by calling functions on the old values and getting a new value. So while everybody's referring to foo, and while foo is referring to this immutable thing, anybody who wants to could be saying, I got a new, better, improved foo, and make one, right? It shares some structure, as we saw. That's the way these data structures work. It can share structure with the one that's already in there. That's no problem. They're all immutable. Nobody who's reading this is impeded by the creation of this new value. It goes on in parallel. And it's not impeded by the fact that anybody's reading. So nobody's in anybody else's way. Then when we want to edit, we want to change this reference atomically to refer to the new thing. And that's always coordinated in Clojure. There are actually multiple semantics. I hadn't said how this happens, when it happens, right? You can have different semantics for that, and Clojure has 3. Anybody who was consuming the value is unaffected. If I was in the middle of doing a calculation on this, I'm still fine, right? So the only thing that of Clojure's data structures that can change are these reference types. There's 3 of them. Refs, it's an unfortunate name in this context, which are about shared, synchronized, coordinated change, right? What's the hardest problem in a system with multiple threads? It's my unit of work touches 3 data structures. In other words, it's a composite unit of work. It's very hard to pull off. So refs do that hardest job. Change 3 things and either have all the changes happen or none of them happen. It uses a transaction system. I'll show you that in a second. Agents are more of a lightweight, autonomous change model where you say, you know what, just eventually do this, and I don't care when. I just want to return right away, and I want you to take care of this job for me. Those things are asynchronous. They're also independent. There's no way to move something from one collection to another with agents. And vars you already saw. Fanfare. Vars you already saw. Vars have concurrency semantics when you set them because they're all thread independent, right? We saw we couldn't set it unless it was per thread bound. So Clojure has something that's called a software transactional memory system. If you've ever worked with a database, this should all be familiar to you. You can only change a ref, and here I'm talking about that STM ref. You can only change them in a transaction, right? Any set of changes you make inside a transaction will happen atomically, right? Your transaction will see a consistent view of the world while it's running, as of a point in time. In addition, Clojure as an STM is kind of unique in supporting consistency rules for the values that you're going to take on. So you have isolation, you have atomicity, and then you have consistency. You can attach to a ref, you can say, validate any data anybody wants to put in here with this function. If that validation fails, that transaction will fail. I won't take the value. You can attach those validation functions to vars, refs, or agents. So they all support consistency. No transaction sees any other transaction. Essentially what happens is your transaction sees the world as if it was a particular point in time. And when you commit, it's as if all the changes you made happened at a particular point in time. The only caveat with this system is, unlike databases, which sort of do deadlock detection and keep guys waiting and sort of have a big lock chain thing, in STM systems, typically, what happens is they're semi-optimistic or fully optimistic. Clojure is only semi-optimistic, which means you can proceed along down your transaction and determine, I am not going to win. I am not going to be able to maintain a consistent view of the world and have a successful commit. So do-over. And that's what happens in STM. So you get an automatic retry, which is great. And it is absolutely what you want. But you have to avoid doing any side effects in the transaction. I can't enforce that, but if you have side effects and you get retried, you'll have your side effects happen more than once. Using this is so simple. Put do-sync around your block of code. Any changes you make to refs inside that block participate in the same transaction, including inside nested functions, including if those nested functions run their own transactions. They all join the enclosing transaction. Under the hood, Clojure's STM is pretty unique. If you've done any reading about STMs, it's a multi-version concurrency control system, which is unusual. Yes?
So should we imagine mutations to refs that aren't wrapped in the desync as participating in just a very small transaction?
No, you can imagine them throwing exceptions. It's a very clear image, too, because that's what happens. That's not okay. Although you can do flying reads, because the contents of any reference is consistent. So I don't care if you read it outside of a transaction. That's perfectly fine. If you wanted to read a bunch of things outside of a transaction and you only cared that each one was consistent, that's also fine. If you want to read a bunch of things and know that they're all consistent as of a point in time, even those reads need to be in a transaction.
Sorry, I'm being stupid here. You said that users have to carefully avoid side effects. I thought
Yes,
this was
in transactions.
I thought this language doesn't have side effects.
Well, you can call Java. You can print. You can read a database. You can.
Yeah, I'm trying to figure out what you mean by the language being functional and not having side effects.
Any language that has no side effects can only heat up your computer, right?
Yeah, right. Exactly.
So yeah, that's not my line. Many times redone.
That's exactly what I was projecting.
Yeah, no, of course, programs do. Yeah, Clojure is a realistic language in saying, of course, your programs do I/O, right? Of course, your programs may want to have identities that are associated with values that change over time. How can I help you do that right? I can't help you with I/O. You have to just do I/O separately. I can help you completely with this data part.
So if you were to send a function to an agent in the middle of do sync, that would be
No. In fact, I haven't talked about agents yet, so hang on to that question. No, that's beautiful.
Could you tell us how you make the first on that?
How you start multiple threads? I don't care. You can definitely use Java's executor framework or thread start or whatever. You can also use the agents, which I haven't gotten to yet.
So in Clojure would be the agent.
If you don't, I don't care. I guess I don't want to say yes, it would be the agents because that's one way, but I'm perfectly happy to use for you to use the executor framework of Java to launch threads. I don't care how they start. Clojure does not require your threads to be adorned by me in any way for this to work. So any way you could start a thread in Java, this will work, including agents, which I'm getting to.
So on the previous slide, you put that note about don't do I/O.
Right.
It's kind of a footnote, but it's a pretty big one.
It's a big thing. It's true of all STMs.
No, but like in Haskell STM, the type system guarantees that you're not going to do I/O inside the transaction monad and whatnot.
Absolutely. I think in a strongly typed system, you can have more enforcement. I'm telling you that I can't in Clojure because it's a dynamically typed.
In practice, how easy is it to shoot yourself in the foot saying, oh, I don't think I'm doing I/O here, well, in reality, you are.
It's the same as anything. This is a dynamic language. So you'll get runtime errors. You'll start seeing things print 3 times and be like, oh, I'm in a transaction. I got retried. And if you're in a dynamic language, you're used to dealing with problems that way. There's no enforcement. I can't enforce it. I'm not anti-enforcement. There are languages that try to enforce it. They come with very intricate type systems that are not yet expressive enough, in my opinion. But that's another way. And if you do that, you could do more. I would love to try to add just enough effect type system to this. to help with that. And that's something that I'll probably research in the next couple of years. But right now, it's on you. It could happen. Okay? So this is pretty cool. This makes sense from a database standpoint. This is a particularly unique thing about Clojure's STM, which is what happens in an STM, right? Well, there could be multiple transactions going on that both want to increment this counter when they're done, right? In most STMs, that means that one transaction is going to win. The other transaction is going to retry, which means doing all their work again in order to get in there. But it ends up that incrementing a counter does not need to be a read, modify, write action. You could do it that way. You could say, look up the counter. It's 41. Add 1. It's 42. Set it back into the ref. It's 42. Now, if I do that in a transaction and somebody else does it in a transaction, one of us will win and the other one will redo. But if you have something that I call commute, you could instead say, you know what? I don't care what value is in there. All I care is when my transaction commits, it's one more than whatever it is. If you have a way to say that, then both those transactions can get all the way to the end, and one could win, and the other could win. They both can win. Neither one needs to retry. So commute is a beautiful facility. It's actually, it was an old database thing called field calls or something. Great idea. And it ends up that you can now build systems with even better concurrency. Because if you only need to end up adding something to a map or end up incrementing something, you can use commute instead of read, modify, write.
So, are you going to give an example of the syntax of commute is to get it more?
Sure. Okay, so what does this look like to use? Okay, we define foo to be that map. Okay, so we have a map. But whoop, it's a reference to a map. Right? Which means if we want to see the value, we have to dereference it. This is just reader syntax for deref of foo. Okay, so just like quote, there's deref and there's meta. There's a couple of other ones that keep you from too many tedious parens. So we deref foo, we see that value. Notice it's in a different order because it's a hash thing, so it's not necessarily what I typed in. I can use that value in calculations. This is a flying read, right? Read the value, associate this thing with it. Have not changed foo, right? I got the value out. Was this a mutable thing? I did some logic on it. I got a new value. This is just that value. Nobody put it back in foo. So that's totally fine. I look at foo, it's the same. I haven't really changed foo. Now I can try to commute foo. The way commute works is it says commute this reference with this function and these values. What will happen is that function will be passed the current state of the ref and those values, and the return value of that function will become the new value in the ref. It's beautiful. There's also alter, which is the read, modify, write. But commute is the one that says, whenever I'm done, do this. So it's nice. It's a functional interface. You say, apply this function to the value that's in that reference. And that result of that function becomes the new value in the reference. So we do this, right? We asked before, can we just do this with a single guy? No. We can't do this anywhere that's outside a transaction. This isn't okay because we didn't start a transaction. This is one in a transaction. Start with doSync. I do that. I could have done a bunch of things inside this doSync, but this is just one. Now this works, and when we dereference foo, we see the changed value. It's pretty easy. It's very easy. And the nice thing about it is you end up reusing a lot of the functions you already wrote. I could test this function right now. I just did, right? In fact, I could do it with any piece of data I want. So because you're applying these functions in transactions, it means you can test these functions on values, not burden your whole system with mock objects and all this other nightmare stuff. Test your functions. You have some data, you're going to apply this function, it's supposed to do this transformation and return this result. Do all that before you get involved in references. There's nothing about that that involves references. Then you say, oh, I want to store these things in references. Okay. All right. So the second, yes?
Are there any requirements that the function actually be a function and not like write any other references inside of itself or any of that?
No, I mean, you can write other references. They all participate in the same transaction.
And if I said it commuted, then it will...
Same thing. You can commute some references in a transaction and alter others. It's totally fine.
So it seems like there's a way to shoot myself in the foot here.
Nope, completely not. Because all those things participate in the same transaction. They're either all going to succeed or none will succeed.
But
So
if I'm commuting
some function call, and the function that is within a commute does some other random write to some other reference.
Oh, the commuting function, no, the commuting function has to be pure.
Do you check that?
Huh?
Do you check that?
No, I can't check it. I'm a dynamic language. That,
Check it
at, yeah, no, no. That's an interesting idea, though, checking it dynamically. Yes, I could do that.
It's a fluid, right?
Yeah, I could do that one. Yes?
I don't quite understand how you implement this kind of in the previous case. So everything I presumed I wrote, which is I wrote into it that says take the value and add one to it, right?
It's already in the library, sure. Right? So you say commute x inc. And that will happen when it commits.
But, I'm worried that your commute is something special, right? Your increment is something special, but your increment is simply add one, right? That's what your increment does, right? I'm just trying to understand what would happen. Put out a reference that had the value inside was 41.
Right.
Right? And that's what initially says. So add foo, commute foo, and then I want to do this lambda plus 1, right?
Right? Yeah.
That's what you're saying, right?
Yeah.
So if I have two guys, right, who've got to read this value,
Yes.
and three transactions happening at the same time, how do
They don't commit at the same time. What ends up happening is commutes get all the way through. Right? Any transaction that involves a commute happens all the way through to commit time. Right? Now, typically, if it's read, modify, write, you'll see the conflict. Two guys try to modify foo. One will win, other one will go back.
Right.
With commutes, what ends up happening is two guys try to commute foo. Second guy in will wait. This guy will finish, he'll go. So he'll do 42, he'll do 43.
Well, that's what I'm saying. How would he get 43? He'll have read that value.
No. Whatever happened inside your transaction in a commute is a temporary value. It's just to make you feel good. At commit time, whatever actual value is in the ref is going to have that function applied to it then.
Right, so then it has to read, suppose you came up with some complicated thing.
It's going to happen twice. It's going to happen twice, and it's a pure function, and that's the cost.
Okay, so then there's no difference from that being saying reading the transaction.
Redo. Well, you could have done 100 other things, though. Let's say you have a really complicated transaction, and it's completely independent from this other one, but both of you have to increment the same counter. Well, if you're really doing that with read, modify, write, you've made both of those transactions completely restart in conflict with each other. With commute, they're not. You do whatever you like. I mean, I'm just saying you have this facility, and it has this property. And you can leverage that in your designs to get more throughput. Okay.
So you could also use this to do I/O conditionally, like say.
No.
I only want to do I/O if I succeed in use commute.
No, do not, no side effects. No. I'm going to give you a recipe for that in 1 second.
If my code is done and I call alter foo
Yes.
early in the transaction,
Yes.
and I do commute foo, does that make the...
That order will work, the other order will not work. I will track when you try to use that commuted value, which is really just a junk value to make you feel good. It can be useful. For instance, if you commuted something that was empty, your transaction would see that it had something in it. If you didn't care about the value that was in it, you could at least see that non-emptiness, which is important sometimes.
So if I commute first and then try to alter it, is that...
You're going to get an exception. Yes?
Is there a way after you commute to find out in which order you have read that you, like after the fact?
You can go back and read,
Okay.
not otherwise.
This has all been worked out in the database world for a long time. It works.
It's very cool, except the software transaction systems you read the papers about don't work like this.
No, it's in the database world.
Yeah, this is very much database driven. MVCC and everything else is really inspired by like Oracle and PostgreSQL and that database stuff. Yes, this is a very databasey kind of thing. All right, let's talk about agents. So agents are for managing independent state, right? We saw transactions are super powerful. They let you change more than one thing atomically, which is very powerful, but it has some overhead to it. Sometimes you just don't care. You want to make a system where you have loosely coupled processes and they just need to communicate with each other. So agents are a way to do that. If you've read about actor model or whatever, agents are sort of similar, but they are not the actor model. In particular, the actor model requires messages to read the values. Agents do not. So you get independent state. You have actions, which are, again, just functions. You say, apply this function to your state at some point in the future. It'll happen in a thread pool. I don't care when. And that will transform your state. They happen immediately. When you call send or send off, you pass this function, you return right away. And then sometime later, that will happen. Okay? And it ends up happening asynchronously in a thread pool. The system makes sure that only one thing is happening to an agent at a time. And it makes all other kinds of great promises. You can dereference agents and see their values, but remember, all kinds of stuff is happening at the same time. You have to start programming that way. If you're still programming from a perspective of, the world has stopped, anytime I want to look at it, you're going to have to change that. When you have 600 cores, you have to start having looser ideas about how much of the world needs to be consistent in order for you to make decisions. Agents let you do that. And what's neat about this is if you send actions during an action, they'll be held. Also, if you send actions to agents during a transaction, they'll be held. So they will happen once and once only when you commit. This is your way to do side effects, because agents can do side effects. So you're doing a transaction. As part of that transaction, you send a message, I'm done. Woohoo! Tell somebody. And that will only go out when you commit. So it's kind of a cool thing, the two systems work together.
Does Clojure itself manage the thread pool with foundation?
Yes.
Okay.
There are actually two. No, not so far, but I probably need to give you some more control to say these set of agents live in this pool. I don't have that now. Right now there are two pools for two different kinds of work. And then again, as I said, they're not actors. An actor model is a distributed programming model. The agent model is only a local programming model, same process. So what does this look like? It looks a lot like the transactions, which is a good thing. We say def foo to be an agent with this map value. We can dereference it. We can see what's in it. No problem. We can send foo. Look how similar this looked to commute blah or alter blah. Send foo a function and maybe some arguments. That function will be applied to the state of foo. The arguments will be passed to it as well. And that will become the new value of foo. If I send this and immediately go and look, it may not have happened yet. Right? It happens asynchronously. Await will make sure anything I've sent from this thread has already been consumed. Then if I look at it, I will see the change. So this is a powerful way to do asynchronous programming. And this is a way to launch threads. Right? There was a question about how do you launch threads? Well, this does things in threads.
You said it only waits for things that got sent from during thread.
Effectively what happens is it puts a message in the queue and then waits for it to be consumed. It's a way to allow you to coordinate. I want to make sure you heard everything before I tell you more. But you have, other people could be talking to the same agent. Okay, this is the last leg. You guys are doing great. Oh, look, we're good. Well, we are pretty good. I'd like to have enough time for some good talk. So I'll try to get through this quickly. So any lingering questions? Now you see all of Clojure. Maybe you put it together. So Clojure is specifically hosted. I haven't shown you much Java stuff, but again, the integration is not a mere implementation detail. I want to be able to call Java. I want to be able to interact with it. Java is my low-level language. And the nice thing about a language like Java being your low-level language is it actually shares the same GC and memory model and threading model and everything else. I mean, think about all those issues you have when you try to start doing multi-threaded programming, or even just GC, the interactions between GC and calling out to C. It's a nightmare. Yeah, I'm sure people are like, it's bad. So JVM is my runtime. I can't say enough about how high quality the infrastructure is in these JVMs. You have a wide range of choices. Right, Sun has their thing, but you can also get, JRocket, and IBM has excellent VMs. I mean, this is a really mature platform with a lot of competition, a lot of extremely bright people working on it. This is excellent technology. As goofy as Java is, the JVM is stunning technology. You cannot ignore it. These just-in-time compilers and these GC systems are the state of the art. Clojure allows wrapper-free interaction with Java. A lot of languages that are hosted on Java, they put their own classes around every Java class. There's none of that. You call Java, you get a Java call. Of course, the other advantage of being on Java is there are absolutely libraries for absolutely every single thing you ever could possibly want to do. And they may not be the best, but they're there. Some are better than others. I'm not saying Java is perfect or anything like that. But there will be choices of libraries in every domain. So what is the integration? What form does it take? There's as much unification as I can possibly make happen. For instance, Java strings are immutable. That's perfectly fine for Clojure strings. They're immutable, they're Unicode. We're done. Clojure strings are Java strings. The numbers I use are the boxed Java numbers. The only thing I had to add to that set was ratio. Otherwise, I use the capital, I integer and things like that. All my collections implement the collection interface of Java. So if you want to use them from Java, you can pass them. If you have a thing that uses collections or iterable, they're all iterable. All my functions are callable and runnable. So you want to use a Clojure Clojure as a callback for a swing, you don't have to do anything. You just pass it because it's runnable. And I showed you before, the Clojure sequence library works with everything Java. Iterable, strings, arrays, the works. You can implement Java classes and interfaces in Clojure, which is nice, keeps you from going there. In addition, I do support primitives, Java primitives, as locals. So if you have a core piece of code that's, your inner loop, where you want to max out the performance, you can make a few little type declarations that say this is an int, this is a long, this is an array of floats, and you'll get the Java primitives that correspond to that. In addition, when you start doing math with those things, you'll get unboxed primitive math. That doesn't mean you'll necessarily get unsafe math. Okay, so there's two different levels. And do I have the boxing, which you turn off with the declaration, and then you're going to have to tell me explicitly, I want bad, plus. And I'll give you bad plus. It ends up that the boxing is much more overhead than the overflow detection. So this is what that looks like. You can access static members just directly. It looks a lot like that namespace syntax, doesn't it? Because that's really what static class members are. They're things in a namespace where the namespace is the class. So I just unify that. You can call methods. This is a macro, ... Right? It says put dots in between everything. You have as many as you want. So it's like we said, system.getProperties.get Java version. And it ends up this has it has fewer parentheses than the Java version. You rapidly have fewer parentheses than the equivalent Java. So anybody from Java is like, oh, Lisp, parens, you just show them this one. Right? Due to a new JFrame, add a new label with hello world, and then pack it and then show it. It has a third of the number of parentheses and lines. Well, it has no lines, it has one line. You can make Java completely easy. And interacting with Java stuff, if you use a sequence library, you don't even know it's Java. You totally don't care. Things like this. This doesn't look like Java, right? This looks like Lisp. Into a map, filter with this. This is shorthand for fun, right? So this is like the most concise lambda expression you can do in Clojure. Do this regular expression fine across. Ooh, this is actually Java. This is the only Java part of this. But it's just transparent. It doesn't turn your Lisp code into Java code. It turns Java code into Lisp code. That's the beauty of it. So don't be afraid, Clojure is Java with parens, because there have been lists for the JVM that went that way. This is what it looks like to do swing, some imports, it's Lisp. This is a callback, right? We're proxying. This is a one-off implementation of a Java interface. It's an anonymous interclass, effectively, you would use in Java. And again, this is so much shorter. The Java for this is 3 times the size. I really like the JVM. It is a great platform. It is a serious piece of technology. My main complaint is the lack of tail call optimization. As I said before, I'm hopeful they'll get that. I can't also say enough about Hotspot. And I'm using Hotspot, which is like some branded thing. There are equivalent ones from IBM and from JRocket and whatnot. But these JITs are amazing. For instance, I talked about that primitive math. Actually, Clojure doesn't emit any of the primitive arithmetic bytecodes. If I can get to a static method call on primitive types, those JITs will finish emitting A, the bytecodes for Java, for arithmetic, and B, turning that into the right instructions for the CPU. In other words, I only have to get as far as a method call, and these optimizers get me to optimized machine code, which runs as fast as C, and often faster now, because they're doing runtime profiling. There are things you can optimize only by looking at a running program, and that's the way these optimizers work. As I said before, ephemeral garbage is extremely cheap. I leverage that. You should too if you're not aware of it. it's great. And there's so many other features. You know, there's verifier, there's security, there's a lot of the ability to load code over the wire. I mean, Java has a lot of stuff under the hood. So the benefits are you can just focus on your language. If you're looking to write a language and want to target this, of course, I recommend just starting with Clojure. But for me, it really let me focus on the language. The infrastructure was great. Sharing with the implementation language, especially these kinds of things, GC, big deal. You get tools for almost nothing. I emit the correct stuff, the correct debugging information. You can debug Clojure, step debug, breakpoints, the whole works. I mean, I'm a LispWorks user. That stuff only came a couple of years ago to LispWorks. You have excellent debugging, excellent profiles, and your choice. All work out of the box with Clojure. And then there are libraries for everything. You know, Clojure users were instantly doing all kinds of stuff I couldn't possibly imagine in advance. They were just talking to databases and doing, you know, net kernel stuff and big document processing, MapReduce, Hadoop, lots of cool stuff. There's also excellent infrastructure on the JVM for implementing things like the STM. This Java util concurrent library is really good. There's a lot more to Clojure. It has list comprehensions, ad hoc hierarchies I mentioned before. With type hints, you can get Java code to run exactly the same speed as Java. So Clojure is fast. I hinted at the relational set algebra and the parallel libraries for doing parallel computations. Automatically leverage all the CPUs to crunch big arrays. And namespaces, there's zippers like Hewitt's paper and XML and a whole bunch of other stuff. Any questions?
So what does generic plus turn into in Java bytecode and then into practice and execution?
Generic plus is, it turns into a Java, you know, type test quickly and then branch to, in my library, individual types, which implement logic for that type. It will do an automatic promotion to the bigger type between arguments.
How bad is the type dispatch in Java bytecode?
The thing is that these optimizers optimize a lot of that stuff away. And in fact, they really can take something where you haven't even hand-coded a fast path, and they'll chop it out, and they'll stick it over here, and they'll say, well, you know, let me just try running that in all cases, and I'll have a little, very inexpensive test I'll use to see if it's still the right way to go, and then I'll slope half the others. So, you know, I couldn't say, because each JVM does different things, but it's pretty fast. The main optimization required moving forward is something that they call escape analysis, where if you knew up a box number and immediately consume it, they should be able to completely avoid that allocation. And that's something that's just coming into the next generation of optimizers for the JVM. So that will help all of these things. And in addition, like I said, if you really care and you need to go right to the metal, you say int x and you're done. No dispatch, no nothing. Ints.
Could you describe your development environment when you're writing in Clojure? Do you use a debugger, specific debuggers, or Vim, or
Use Emacs. There's Emacs plugins. There's Slime. There's all kinds of cool stuff already ported for Clojure. There's an Emacs mode. There's a VI mode, which is not as sophisticated. There's an environment for NetBeans, a plugin for NetBeans, which has syntax highlighting and everything else. That has the best debugger support right now, the NetBeans plugin. But you can use any debugger. You can use JSWAT or GDB or whatnot, profiled with YourKit, which is just gorgeous piece of technology. Really, all the tools work. But in terms of editing, I edit Java code with IntelliJ, and I edit Clojure code with Emacs. And I don't debug.
Just about to ask, is there a Clojure language level debugger?
No, I'm not going to do that because these debuggers are so good. Oh, these debuggers, when debugging Clojure, debug Clojure language. When I'm saying breakpoints and stepping, you're stepping through Clojure code. You're setting breakpoints in Clojure code. Clojure emits a mapping file and line number information that's necessary for Java debuggers to say line 42 is over here in the Clojure file.
If I'm typing away at the REPL and somewhere down inside somewhere I take car of 5,
Right.
it says, no, you don't want to do that.
Attach a debugger. You can attach these debuggers. You don't have to be in debug mode in Clojure. If you start it with the debug API live, you can attach a Java debugger to it whenever you want, including right then. But I'm not going to re-implement Common Lisp style debugging because this stuff is, it's not the same, but it's really good, and I don't have time for the other. If somebody wants to, they could, but.
You said you've also programmed in C#.
Sure.
The .NET platform has scaled knowledge up to.
Yeah, they don't always do it though.
I don't know, but at least it's there. They could always do it later. Is there
Right. Well, that later is still. I'm waiting for later too.
Is there anything in Clojure other than STM stuff? Let's just say because .NET doesn't play with the C.
No, I started Clojure for both platforms. Clojure ran on both platforms for a long time. I just got tired of doing everything twice. I also wanted to make a decision about what will library authors do? How will the library for Clojure grow? And as much as I'm expert enough to do C# and Java, and many other people are, everybody isn't. And it's a big thing to take on, having to do everything twice and do the least common denominator and everything else. So I abandoned the C# report maybe 2 years ago now. It certainly would be possible to do. Yes, C# has everything you need to do this.
Right. How long have you been doing this?
3 years. It's been out since last October, so it's coming around a year. It's really taking off. I mean, I have a big group of users. I have over 500 people on the mailing list, and we get 500 or 600 messages a month, and I have thousands of SVN hits a month. So I think I have a couple of thousand users.
What would you say the most interesting uses are from that you've heard of anyway?
Well, I don't hear from people unless they have a problem. So I wish I knew. I do know there's a couple of companies using it, and it's sort of like their secret weapon thing. They do document processing and some other stuff. I've seen interesting database work. I've seen interesting graphics work and XML things. There's some really neat stuff. Like there's a zipper library which allows you to sort of pretend you're manipulating something in a destructive way when you're really not, and producing a changed version of a data structure. And somebody wrote a really neat, like XPath-like way for processing XML functionally with that.
How large is the runtime?
Excuse me?
The runtime, how large is it?
400K.
400K.
Fits on a floppy disk. If you could find a floppy disk. And half of that is the ASM library that I use to emit the bytecode. Clojure is about 250, 300K.
You've listed Common Lisp, Oracle, and standard ML, I think, as influences. Anything else?
Sure, Haskell and all the STM work and basically anything I could get my hands on to read. A lot of database stuff went into the STM. That old Andrus Writer book or whatever, which will make you really never want to use a database that's not MVCC ever again. Really, whatever I could get my hands on to read. I like to read.
I'm just curious, what would be your capsule comparison of Clojure versus Scala?
Clojure versus Scala. Well, Scala is statically typed and has one of these sophisticated type systems. I think Clojure is more strictly functional because it defaults to immutability and defaults to the data structures are these persistent data structures. It also has a recipe for concurrency built in. There is some library work for that for Scala, but Scala is really still a multi-paradigm language where the objects are still those old share the reference to the block O memory objects, and I think that is doomed. Yes?
So you mentioned running on these SLs, like 600 core labs.
Yeah. I highly recommend it. It's so much fun.
Yeah, so let's go get one. But, I mean, does the performance actually scale fairly linearly, or did the
Well,
Java
they found,
start to...
well, he found it did on this problem. Of course, the whole thing with STMs, everybody's like, STM is this holy grail, and when you try to say something's a holy grail, well, it's going to fail, right? Because nothing can do everything. You still have to architect your programs. You still have to have some sense of what is the contention profile of my program. You still may run into performance bottlenecks that you have to solve by changing the contention profile of your program. I mean, it's not a silver bullet. What it is a way to write something that's correct easily, and the tools for doing that. But there's still going to be, work.
But so the moral is, like, by at least being sort of idiomatic, you probably can add 100 times more cores than you have, and it'll be okay. I mean,
If you've ever written programs with locks, I mean, you can be wrong on 2 cores. right away. You can be wrong on one core. It's so easy to be wrong. It's so easy to be wrong.
You explain your logo?
My brother did it for me. It's
What's
pretty.
yin-yang?
It's a little yin yang, a little lambda. Yeah, he's good.
So, laziness question. So
Yes.
In Haskell, it seems like any time a Haskell programmer runs into a speed or space issue, goes through, makes everything strict.
Right.
Have you found out with Clojure? Have you gotten around it? Did it just not happen?
It's not the same thing because Haskell, everything is lazy, right? So that's a big difference. When everything is lazy, it's very difficult to tell when you're going to have this explosion in memory requirements, and that's the problem people run into with Haskell. With Clojure, the laziness is limited to these sequences. And in particular, I'm very careful that inside a sequence operation, as you move through, which is usually you're doing, usually you just, maybe you have a concatenated set of operations, but you're walking that window through your data set. I make sure by cleaning up the stack that you don't retain the head. It's easy to retain the head accidentally in Haskell, in which case as soon as you realize this thing, you've realized the thing. As soon as you've walked it or touched it, you have the whole thing. In Clojure, you walk it, you don't have the whole thing. In fact, it can erase as you go. I mean, it can get GC'd as you go. So I haven't seen that be a problem. In fact, I think the laziness is a real attribute in the low memory utilization of Clojure programs.
How much of Clojure is written in Clojure and how much is written in Java?
It's about 15,000 lines of Java and 4,000 lines of Clojure. Absolutely. In fact, when you define a Java class in Clojure, you end up with a Java class that's extremely dynamic, much more dynamic than a regular Java class. In fact, all it is a set of stubs that hook into Clojure vars. So you can, no, it's not funny. It's very powerful. No, you can write Java classes in Clojure that you can fix while they're running. You can fix the definitions of methods. You can also write transactional Java objects in Clojure. You can write Java objects in Clojure whose data can only be changed inside transactions.
Great.
It's cool.
I was a little surprised by your answer about the source code being three-quarters Java.
Yes.
Are you planning on moving towards a system that's more bootstrap?
Well, you know how it is when you have something that works. There's a reason that the data structures are written in Java and the interfaces are written in Java, and that's so that consumption from Java is straightforward. Clojure does not yet have all of the mechanisms in Clojure's Java emitting syntax to do the lowest level, like field type declarations you need for the highest performance classes. And I'm not sure I want to go there because it'll end up being Java with parentheses. By the time you have private, protected, whatever, and all the declarations you need to support exactly what you would do in Java. So the biggest thing that's in Java that probably I would like not to be in Java is the compiler itself, which is about 4,000 lines of Java. And people have asked about bootstrapping that. That certainly would be possible to do. It's the old, it's working right now kind of problem. And I'd rather do new things. So I don't have a big thing. I mean, I know it's like sort of a chest beating, proof of whatever. I really just don't care. You know, some people have tried to do that. I mean, unfortunately, even 450K is a bit much. But one of the other challenges is just that I do need a fair amount of Java concurrency mojo. Like, I only go as low as Java 1.5 because I need a lot of the Java util concurrent stuff to support some of the things. So that's definitely something I'd like to do. Another thing that's tough on the mobile phones is dynamic code generation. The bytecode loaders and some of the things are secured that way. One of the things on my to-do list is ahead of time compilation to bytecode, which will let me target some of those static platforms like Google, Android. So there's that. Yes?
There's a standard problem with promises in Steam that make streams mildly annoying when you filter out of all of the integers numbers that are larger than 10 billion, and then you try to get one of them. You end up with, if the promises were implemented naively, you'd get a string of 10 billion promises that would all have to resolve before you saw the first value. You do the appropriate trampoline.
I don't do it that way. No, that will walk through and just like I said, just describe. You'll have to walk to get to 10 billion, but it's going to throw everything away on the way.
So
It's not a chain. There's no realized chain. If you haven't hung on to the first thing, you don't have it. If you say drop 10 billion from cycle whatever, and then take 3, you'll have those the head of that 3, and you won't have 10 billion anything. It's not a chain of promises.
So there's a trampoline.
No, it cleans up as it moves. That's the trick. What happens is there are suspended expressions, yes, in the head. When they're realized, they're discarded. Now the realized versions are cached. Now we move to the next. Now we have new expressions. Now we evaluate those. Now the expressions are let go of, the values are there. In addition, if this was held on the stack and this is a nested call or some reduce or something like that, no one else is looking at this. We erase the reference to this. Boom, what's left? 1 guy, 2 values. No lingering anything. So no is the answer. It doesn't build up.
You said you could get rid of Haskell.
No, I can't talk about Haskell's implementation. All I can say is it is a known problem with some Haskell programs that the laziness has these interactions that make it difficult to predict the memory usage of your program in advance. I'm saying in Clojure that's not the case because the laziness is limited to these sequences, and I've just told you their behavior that makes it so that they don't accumulate anything that you haven't asked to hang on to. If you hang on to the head and then go 4 billion next and it rests, well, you're now holding on to a 4 billion item thing. But you didn't have to do that, and I will do that accidentally for you. Anything else? Yes? Yeah, it is. There is hope. Right now I have the same that Java does. It's the same thing, arrays or arrays of arrays. Multidimensional arrays or arrays of arrays. But I've seen some cool stuff in IBM's X10 language where they take like a giant array and then they pretend it's multidimensional even though Java doesn't support it. And they have some very neat syntax for using little tuples to do subranges and to do multidimensional indexing. And I was inspired by that, and maybe if it comes to it, I may copy something like that. That is the neatest I've seen. It gets around those problems.
Maybe any closer to finding a
Data log. Anybody know any good data log implementations? Yes, I'd like to add some, where Clojure is going is I'd like to add some declarative data access stuff. Not really Prolog, because it's not that great for database work. But data log, which is sort of a subset of Prolog for which a lot of research has been done in optimization, would be a good mini rule system plus data access that's pretty. It supports recursion and things like that. So I'm still researching whether I'm going to roll my own or use Iris Reasoner, which is a Java one that's open source. Maps. Yes, there is actually something called a struct in Clojure, and it's an optimized implementation of map, where you say, I know I'm going to have 10 million of these things that are going to have fields A, B, and C. So repeating A, B, and C in all those little maps is kind of a waste of time. So I can make that go away. But it still implements the map interface, and for all intents and purposes, it is a map. You can still add extra stuff to it, just like you do. You can still associate. So it's nice. It's the best of both worlds.
And for multiple values, you use maps.
Multiple values, you do whatever you want, but I don't have them on the stack. I can't do them. Clojure is stack compatible with Java, so there's no multiple returns.
Was there any interaction that we should know between metadata and transactions?
No. No, I mean, like I said, most of the transformative functions of values will be metadata preservative. So, and you're just going to pass a function to the transaction to say modify the value with this function, which will be something like a soc or something you wrote based on a soc. It'll still preserve metadata. Metadata is very neat. You can do multi-methods that key off metadata. So do this if it's data I don't trust. That kind of polymorphism is something we need. And doing everything with types really has limited us.
Also, I read that at the JVM Summit there's some talk about a mock for these dynamic languages similar to the .NET.
Yes.
Did you learn anything interesting that
I learned that those guys need to learn a lot more about languages that aren't a lot like small talk. No, I mean, their first cut is to try to support the popular languages there, which are JRuby and Jython, which have very similar object models. So they have a distinguished receiver and stuff like that in the mop. And I did try to tell the guy, look, just move the parenthesis over and let's just realize it's all functions. Can we just do that? There's really no such thing as methods.
You made a comment on the discussion board about how basically having all the defins end up in the permanent generation wasn't a big deal. Can you elaborate on that? Because I sort of didn't see where you were coming from.
All the defins end up in the permanent.
Yeah, so there was a thing whereby so you do a def and it gets implemented as a class, right?
Oh, the classes, right. Well, in other words, some of these languages need to generate tons of classes in order to, like, for instance, do those wrappers. I said Clojure has wrapper-free access to Java. A lot of these languages don't. In addition, a lot of these languages have, they're like Ruby and Python. They're written by guys who were writing something fun for themselves. They weren't thinking about compiling those languages when they wrote them. Now, these Java guys doing Jython and JRuby are trying to compile them, and it's very challenging. So one of the things they're trying to do is, polymorphic inline caches and all that stuff. And when they generate any code in Java, you have to generate a class. So that's the unit of code. So they are doing a lot of ephemeral class generation, and classes have an impact on this perm gen. Clojure really doesn't do any of that. Yeah, which is not that many. Unless you really need to fix that function a lot. You should be okay.
Or you're doing genetic programming?
Excuse me?
Or you're doing genetic programming?
Well, those things are all compiled. So even if you see funds, that's not like a new class at runtime. It's a class at compile time. So that's the stuff that they're talking about. Yeah, if you were writing generic programs, right, and you need to do a lot of evaluation of function definition, sure, you would get into perm gen issues. Yes. Yes.
Do you have any advice or hints about what sort of applications do you think would shine in Clojure? Something that would use both the Lisp side and the concurrency?
I think anything. I mean, right now, if you want to write a program, Clojure is designed to be useful anywhere you would use Java. And Java is being applied, people already asked about phones and these 600 CPU machines, so it's a wide range. It's the same question for Lisp. What is Lisp good for? Pretty much anything.
What would be dramatic? What would work really well in a 600 core machine and blows other people away?
Anything that you can think of a way to parallelize. By the time you get to 600 cores, I actually think most applications will never be able to leverage 600 cores. There'll be certain kinds of things that can, and most applications, I talked about that task parallelism, most applications will be able to number their tasks in the low dozens, I think, really. So the job of those mega machines will be to run multiple of those applications. The main thing for Clojure is you can write that multiple dozens of tasks, parallelism, without error. And in terms of application domain, every application I've ever written has needed to do that and struggled to get it correct. So I think it's good for a wide variety. I wouldn't want to pin it down. Yes?
Can you talk about your STM implementation? Does for instance, does your compiler have a special case, sort of, I'm inside a transaction, so
Nope.
different stuff?
No, it's a runtime thing in a transaction.
So how does it?
It's a thread local thing that we're in a transaction, so because the transaction is going to be in a thread. And then the transaction starts in the thread, and there's a transaction object. References, all interaction with references is going to test for the presence of that object and make sure that you are in a transaction. That's how we got that exception before.
Okay, so we're explicitly going through references.
You have to go through references. That's the beauty of this STM. You have to have identified the things that can change. Either they're in an agent, they're in a var, or they're in a ref.
GC references.
Right.
That's where you monitor the rights and
Correct. Multiple questions. Yeah,
that's where you track the writes and reads in order to do the concurrency.
Correct, except I do not track reads. Clojure's STM is unique. It does not track reads.
Right,
Right, it's MVCC. I looked at that. I actually think that the condition system is in a hard-coded special case in Common Lisp. That if you had some more general primitives, the condition system would just be one thing you could implement with them. In Clojure, you have two things you can utilize to help you with those kinds of problems. One is the exception system, which allows you to travel up and down the stack. The other is that dynamic binding of functions. You want to have a function. I'm going to bind this function to something that you should call if you have a problem. Well, now you've got that ability to call some code from above down low to see what you should be doing. Combining dynamic functions and exceptions gives you some of the condition system.
But it doesn't do response. You can't, once you throw an exception.
But you don't throw an exception. That's what I'm saying. Let's say you're somebody who needs to talk to the file system, right? And you say, if I have a problem talking to the file system, I'm going to call, I had a problem talking to the file system. Somebody above you can bind that to do whatever you want. You're going to call that, use the return value, and not throw. Right, and so I think that gets you most of the way there. Dynamically rebindable functions and exceptions, I think, is enough. I like the condition system, but it seems to me to be a hardwired special construct rather than two.
It's just throw.
Yeah. Right.
It's throw it back.
Yeah.
Do you think it's important to have all functions be dynamically rebindable for that to work, or is the important thing just the presence of dynamic variables?
You know, I've looked at whether or not you should, instead of having everything be potentially dynamic, you call out the things that you're going to allow to be dynamic. And the problem with that is, you don't know. Now your program's running and you say, oh, we're having this problem in here. I wish I could log this function. Well, you didn't declare it dynamic, so now it's stopped the running system. And so rather than do that, I've made it so that all vars are potentially rebindable. And I think that's a better way to go, only because I was able to make the check extremely inexpensive so that you can incur it everywhere. So far, that's worked out. The cost of calling them out would be, you couldn't, on an ad hoc basis, say, oh, I wish I could dynamically rebind this. Yes?
I take it you don't have first-class materials?
No.
Someone had to say this.
There was talk about it at the JVM. I mean, if the JVM supports them, I don't know why I wouldn't. But otherwise, I think they're too complicated for me. Continuations. No. No.
Thank you.
You're welcome.
The way the symbols and with all that, you don't think there will be implementation of macros on this?
No. I mean, I think the system is good. If you're coming from Common Lisp and you get your head around how this is different, you'll see it does get rid of, I think, 80+% of the hygiene issues. Really, just go away. Because when this macro was written, list meant the list function in Clojure. It will emit something that will make sure that gets that binding. And that is what hygiene is about. But it doesn't have a sophisticated renaming system.
What would you want, a sophisticated renaming system?
I also don't understand those too well. Especially the implementation. There's like this sourdough implementation of that, right? And no one ever re-implements it. Everybody just passes this one thing around, which means if your language isn't Scheme, you have to, what do? Right? I seem to see this one implementation of hygienic macros reused, let's say, everywhere.
It's a beautiful metaphor.
It's complicated.
Do you have a white paper for something specifically on macros and
No, just the stuff, just the material on the site. There's a lot of material on the site. But we have a good group, and any question or dialogue you start will inform everyone. So I encourage anyone who's using Clojure to join the Google group, and I'll be happy to expound on any details. All right. Well. What's Zipper? Some French guy whose name I can't quite pronounce. Huet, H-U-E-T, wrote a beautiful functional Perl on zippers, which is a way to navigate through a tree-like data structure as if it was imperative. And you can go through and you say, boom, and get here and say, replace this with something else. And then you can say, up. And you go back up to the root of the tree, and what you have then is a changed thing. There's an implementation of that here in Clojure.
I think we should probably stop taking questions at this point.
Okay.
So
Thank you very much.
I'm going to thank you very much.